In this lecture, we will understand how to store arrays in memory. Here is a simple C statement. It's accessing the element I of the array A and writing the value of that element into a variable X. In order to produce RISC-V assembly code for this statement, we need to know where are the variables xi and the base of array A. So let's say that x is in S3, I is in T0, the base of the array A is in S6. Remember that the base of the array is the address of the element 0 of the array, and this is an array of integers of 32-bit integers. So here's our assumption. Here is S6, and for this example, let's assume that S6 contains the address 0x7500-0004. So here's our memory. Let me get out of the way. And in our memory, we are increasing the addresses by 4, which means that each one of these boxes contains 4 bytes or 32 bits in this representation. The first question is, where is A0? Remember that A0 is the element that is at the address of the base of the array. The address of the base of the array is in S6. Therefore, the element A0 will be at this position in memory. So we can say that the element A0 is at the address in S6. Where is the element A1? The element A1 is the next element after A0. Therefore, it will be in the position immediately above A0, above A sub 0, and it will be then at the address S6 plus 4. And where is the element A2? Of course, the element A2 is the next element, so it will be at the address S6 plus 8, and so on. And where is the element A sub I? The element A sub I, we can, following the pattern, will discover that it is at the address given by S6 plus 4 times I. Therefore, if we want now to bring from memory the value of A sub I into S3, what we need to do is to multiply I by 4 initially and write the result in a temporary. And in this notation here, I'm using TA, which is not an existing register in RISC-V. Whenever I'm writing pseudocode, I use these symbolic registers. I will later translate them into the actual registers in the processor. It's just a convenience of developing code this way, starting with this intermediate representation. Next, I will take the value that I obtained by multiplying I by 4 and add to the base of the array, which is in S6, and I will produce the value in a new temporary. And finally, I will go to the memory position, whose address is given by this temporary TB, and obtain the value and put the result into S3. This is what the C statement is doing. So that's my C statement again. In red, I have my pseudocode. It's not real assembly. It's just a code that I wrote to remind me of what I need to do. Now I can easily translate that pseudocode in assembly by selecting registers in the processor to write the temporaries. So I was in T0, so to multiply I by 4, I'm going to use a shift left logical immediate SLLI of 2, because shifting to the left by 2 is the equivalent of multiplying by 2 to the power of 2, which is 4. I use this for a multiplication powers of 2 because the cost of a shift operation is much lower than the cost of a multiply operation. Then I will add the value that I obtained from that multiplication to the base of the array by adding T1 to S6, obtain the value in T2, and then I will load the value from the memory position given by T2 now with a displacement of 0 and put the result in S3. At this point in the lecture, it's common for students to ask me, why couldn't I have used the value of T1 as a displacement in the load word instruction? Instead of doing the add S6 T1, why don't I use T1 S6 here in the load word instruction to address memory? The reason why I cannot do that is because such addressing mode does not exist in RISC-V. It exists in other architectures, but not in RISC-V, and it does not exist in MIPS either. So I have to do the addition before accessing memory. So here I have a variation on the same example, but in this case, I taken the value of a variable x and writing that value in the position I of the array A. Before I was reading from the array and put into a variable. Now I taken the value of a variable and put in the array. The access is very similar. I need to compute the address by multiplying I by 4 and adding the result to the base of the array A. And then now I'm going to be doing a store operation because I need to write from the register S3 into the memory. So the only thing that changes here, instead of a load word, I have a store word now. And now the S3 is the source for the store word, and the memory position whose address is given by 0 to 2 is the destination. Here is a new example where I now taking the position K of an array called name and put into a variable C. The difference now here is that this array C is an array of 8-bit characters where 8 bits is equal 1 byte. Everything else is similar. I have the registers where I have the variable C, the index K is in T0, and the base of the array name is in S4. So the difference now is because each element of the array name is a single byte, the distance between two consecutive elements of the array name is 1. Therefore, if I want to find the position K of the array name, all I have to do is to add the value of K to name to obtain the address. There is no need to multiply K by 4 because I don't have the same phenomenon as before where each element of the integer array had 4 bytes. And now to load that value from the memory, instead of using a load word operation, I will use a load byte operation because the load byte operation will bring a single byte from memory instead of bringing an entire word. So whenever manipulating strings, for example, I'll be using the operations load byte and store byte instead of the load word and store word. Here is a more complex piece of code, but still we're going to be using the same techniques as before. What happens here is that I wanted to fetch a position of an array A, but the index that I'll use to find that position array A is the value that is stored in the position J of an array B. So I have an array B, I have an array A, and I have an index J into the array B. So I will use that index J to find the position of the array B where I need to fetch a value from. When I obtain that position from the array B, I will use that result to find the position in array A, and when I get that value, then I'll put into the variable Y. So again, I need to know where each one of those variables are. Let's assume that Y is in S3. Let's assume that J is in T0. The base of the array A is in S6, and the base of the array B is in S7. Now, to obtain the element B sub J, I will do the same that I did before. The other thing that I need to know is the size of each element of these arrays. Each one of those arrays is an array of 32-bit integers, so each element is 4 bytes. So if each element is 4 bytes, what I need to do is take the value of J and multiply by 4 to obtain 4 times J, and then add the result to S7, which contains the base of the array B, and that will give me the address that I'll use to go to the memory and find the value of B sub J. Once I have the value of B sub J, I need to now multiply the value of B sub J by 4 and add the result to the base of the array A, which is in S6, and that will give me the value A sub B sub J, and I'll then write that value into S3, that is where the variable Y is. So the risk code to do this will consist on multiplying j by 4, which I do by doing a shift left logical immediate of 2 into t0. And I put this into a temporary t1. Then I'll add the value that I obtained from that multiplication to the base of the array B. Next, I'll load from memory from that address that I just computed. That will take the value of bj and put in my temporary t3. Now I will multiply the value that I obtained from memory by shifting it left logical immediate by 2, and my new temporary is t4. And then I'm going to add the value of this temporary to the base of the array A, which is in S6, to obtain then t5. And now I can load from that memory position and put the result into S3, that is where y is. So this more complex example is just to illustrate that the expression that I use to obtain the index of an array can be complex. And when I finish doing that computation, I still need to do the multiplication by 4 and the adding to the base of the array. So here's a recap of what we learned in this lesson. First, we examined memory, and we saw that when we store an array in memory, an array of integers, each integer occupies 4 bytes. We saw that the base of the integer array is the address of the element 0 of the array. The distance between two consecutive elements in an integer array is 4. And I can find the address of the element I of an array of integers by computing the value 4 times I, which I do using a shift left logical immediate instruction. We also have seen that I may have arrays that are arrays of characters. And if I have an array of characters, each character is only 1 byte, and therefore, when I have an array of characters, I do not need to multiply the index by 4 to find the element name sub k, for example. This is what we had for this lecture.